So today's lecture would be on empirical device models. The previous lecture we discussed what a model was, uh, why we use models instead of dealing directly with physical devices. We learned that a model is a simplified representation of reality, and in that choosing the right model is essential to engineering skill. We so this lecture we take the discussion one step further by asking the important question: what kind of model are we using? So not all models are created in the same way. Some are based purely on observations and measurements, and while others are built from an understanding of the underlying physics. So in this lecture, we'd be focusing on the first kind, the one that's based on observations, and the first kind are known as empirical models. So what is an empirical model? So as we can see from the etymology, that an empirical model is one that is derived from experience or experiments. So the word empirical itself means that it's based on observation or experimental data rather than on physical theory. So, an empirical model is developed by measuring the behavior of a device, recording the results, and finding mathematical equations that match those measurements. So, we notice that the process does not require us to know what is happening inside the device. As long as the mathematical equation reproduce the measured behavior, the model is considered acceptable. So let's take the example of the bipolar junction transistor. So we know that um, uh, to represent the terminal characteristics, we have the input output characteristics. So the input characteristic shows the relationship between the base emitter voltage and the base current, and the output voltage shows the relationship between collector current and the collector emitter voltage. So these graphs describe how the transistor behaves from the outside, but it does not describe or explain why it behaves that way. So um, we have two kinds of transistor models. One is a large signal model, and the other is the incremental model. So coming to the large signal model, the large signal model describes the transistor's overall operating behavior. So it is useful for analyzing DC biasing, operating point calculations, and switching circuits. Whereas the incremental or small signal model, how the transistor shows us how the transistor responds to small changes around a chosen operating point. So this is used for amplifier analysis, AC signal analysis, and gain calculations. And both these models are extremely useful for circuit analysis. So, an important question at this point we have would be that if we already know the transistor characteristics and we have these circuit models that exist, why do we need to study semiconductor physics? It is a reasonable question, and after all, if the models work, why learn anything more, right? So, the answer lies is we want to understand how these models were created. So, uh, to develop empirical models, so say we have a new transistor. The first step is to perform laboratory experiments and take measurements. So we measure things like the voltage, current, and operating characteristics, and under many different conditions. And next, we search for a combination of ideal circuit elements that reproduce the measured behavior. So, for example, we may use diodes, current sources, and resistors until the circuit behaves similarly to the real transistor. If the terminal currents and the voltages match the measurements reasonably well, we accept the model. So we need to notice something important here. The model is built from outside looking in. We never ask what is happening physically inside the transistor. We simply reproduce the external behavior. This is the essence of empirical modeling, right? So, however, an interesting feature is that with empirical modeling, there often is more than one correct model. Different combinations of circuit elements may produce the exact same terminal characteristics. For example, model A and a model B may both predict identical collector and base current. And from external measurements alone, there may be no way to determine which model is better and represents the actual device. This shows that empirical models are not unique, they are mathematical approximations. And rather than physical descriptions. So, given all that, empirical modeling definitely has a few limitations. So, the first one we can talk about is that they do not explain the physics, as mentioned numerous times. So, empirical model tells us what happened, but does not tell us why. And for example, say we have a transistor model that contains a diode at voltage drops of zero point 0.6 volt and zero point 0.4 volt. And the model reproduces the measured behavior. However, it does not explain why it's zero point 0.6 or zero point 0.4 or why not zero point 0.5 volt or zero point 0.8 volt. The model provides no answers. Another limitation that we are talking about is they cannot predict design changes. Say we want to build a transistor with a high current gain of beta. So an empirical model tells us the value of beta, but it cannot tell us what determines beta or how to change it. Without understanding the device physics, the model cannot guide the design process. So another limitation that we are addressing is that they cannot predict new operating conditions. Say someone asks what happens if the temperature increases, or what happens if the frequency increases, or if in specific if they ask us what happens if the transistor operates at 1 gigahertz specifically, or we cannot tell what happens with a specific current, say 100 amps. And a empirical model cannot confidently answer these questions unless we have specifically conducted these experiments before under those exact conditions. So the predictive ability is limited to the situations that have already been tested. So what you've seen is what you've got, right? So a good way of putting this is that what you've measured is what you know. So if you want to know how a device behaves under new conditions, you must perform new experiments. And every new operating condition requires additional measurements. This makes empirical modeling expensive, time consuming when designing new technologies, which is what we are ideally interested in, right? So, why study device physics? So, instead of relying only on measurements, we want models based on physical principles. So, a physics based model, say, explains how the electrons move, how electrons move, how the electric fields are formed, and how the charge carriers interact, why current flows through a device. Once we understand these physical processes, we can predict behavior under new conditions that have never been tested before experimentally. So, given that, there are definitely advantages of physics based models. Uh, they allow us to answer questions like how will the transistor behave at high temperatures? What happens if the device dimensions become smaller? How can current be increased? What limits the operating frequency? Or another important question is that does one transistor perform better than the other? So instead of building and testing every possible design, we can use the model to predict performance before the manufacturing the device. This greatly reduces development time and cost. So, what's the goal? The goal of studying semiconductor devices is simply not to memorize transistor models. Instead, the objective is to understand the physical mechanism inside the electronic devices. And once those mechanisms are understood, the commonly used circuit models become much easier to understand. Their limitations become clear, and new models can be developed for new devices and technologies. So ultimately, physics-based model give us something that empirical models cannot: the ability to predict the unknown. So just basically summarizing, an empirical model is a model developed from experimental observations rather than an understanding of the underlying physics. And empirical models are valuable because they accurately reproduce measured device behavior and are widely used in circuit analysis. However, they have important limitations. They explain what a device does, but not why it behaves that way. They cannot reliably predict performance under new operating conditions, and they do not really help us design improved devices. So, to overcome these limitations, we develop physics based models which are derived from the fundamental behavior of charge carriers inside the semiconductor material. These models provide a deeper insight, they explain observed behavior and enable, this is the most important part, they enable the prediction and design of new electronic devices, which is what we strive towards. So, that's it for today.